Wormholes promise the potential for faster-than-light travel and communications. They're also profoundly weird deviations from the ordinary rules of space and time. Now, new experiments are beginning to give us a peek at how these strange objects can be used for teleportation. Not all wormholes are created equal. Some are non-traversable because you would have to exceed the speed of light to traverse it. But there are also traversable ones that can be potentially stable if only we could discover some kind of matter or energy that would hold one open. To build one, you just need to entangle two black holes such that they share a single quantum state. This quantum entanglement ensures that whatever affects one will affect the other. Then you send a message in one end. It becomes completely scrambled as it travels through the black holes, merging with the entangled matter inside. Then, as if by magic, it emerges from the other end completely intact. While it may be impossible to construct entangled black holes in a lab, it turns out that it is possible to build the next best thing, a set of trapped, entangled ions that serve as a mathematically equivalent stand-in for the wormhole. And a University of Maryland team has done just that, showing the realization of an amazing theoretical prediction of quantum mechanics, as well as opening the door to investigating quantum gravity in the lab in a tabletop experiment. The theoretical prediction in question is how information in a quantum system is transmitted, or in quantum parlance, teleported. It turns out that it is much the same as in ordinary systems. Information can be encoded into a chaotic system and then be extracted. You can think of this as sending information with your voice that is encoded in the motion of many, many molecules of air. No individual molecule contains all the information. Rather, it is the collection of molecules that transmits it. Once the molecules impact an appropriate receiver like the human ear, the information is reconstructed out of the chaos. Quantum systems can behave in this way as well, with information encoding a particular quantum state being spread throughout many chaotic quantum particles that are entangled. The quantum information can then be reconstructed from those by a quantum receiver, resulting in effectively the teleportation of the original quantum information. Schrödinger's equation can explain this phenomenon with a lot of mathematical manipulations, but there is a simpler, intuitive physical explanation: the passing of a message through a pair of black holes connected via a traversable wormhole. How to build a wormhole. Theoretically, two black holes can be connected so that if Alice falls into one and Bob falls into the other, they can actually meet inside, even if they were originally separated by light years. These black hole pairs share a singularity, like two ears that share a brain. They are sometimes called a two-sided black hole. In space, these would literally appear to be two black holes with nothing in between them because the connection is outside of ordinary space. Wormholes are frequently erroneously portrayed in science fiction as being like tunnels with entrances that magically appear or disappear on command. The reality is that a wormhole is a four-dimensional object with two spherical openings that stick around as long as the wormhole exists. Ordinarily, objects, people, or messages falling into one or the other would hit the singularity and never emerge from one or the other side. Thus, these form a non-traversable wormhole because although information can travel from one to the other, it can never emerge. To change that, something special has to happen. A traversable wormhole forms between the two when a quantum coupling exists between the boundaries of the two black holes. You can think of this as being like a ladder of entangled energy connecting the two boundaries. This quantum coupling violates a principle called the average null energy condition, ANIC, that relates to the average energy along light-like paths in a space-time geometry. Having negative average null energy is a requirement for a traversable wormhole. This condition is violated by some quantum effects like the Casimir effect, in which two plates held close together experience a force pushing them together because of negative energy in between them. Violating the ANIC does not, however, allow you to travel or send messages faster than light. In order to do that and potentially violate causality, you would have to violate a stricter condition called the average acronal null energy condition, ANIC. The Casimir effect does not violate this condition, and it has been proved recently that no known quantum or classical matter or energy violate it. This condition might be the ultimate traffic cop in the universe, ensuring that while wormholes can be built or discovered, they can't help you go faster than light. On the other hand, it doesn't mean that traveling through the wormhole necessarily takes a long time for the message or person traveling through it. All it means is that the teleported object will arrive no sooner than the same object sent at the speed of light the ordinary way. The quantum coupling between the black hole boundaries creates a negative energy gravitational backreaction that allows information inserted into the boundary of one black hole to emerge from the other. In order to do this, the information falls towards the singularity but is interrupted by the backreaction like an updraft interrupting the fall of a hang glider. The backreaction carries it back towards the other black hole's horizon, effectively carrying the information back in time, the only way information can escape a black hole. The information emerges from the boundary and then leaves the backreaction traveling on into the future. For a person teleported this way, the black hole would scramble their body and brain and eject it at the speed of light in the vicinity of the other black hole. They would thus re-emerge, completely reassembled as if no time had passed at all, with some likelihood of failure and the grotesque consequences thereof. Whether a person could be encoded this way so as to maintain entanglement with the negative energy stream is beyond current physics. They would either have to be copied into the stream or replace an existing part of the stream without collapsing the stream and closing the wormhole. Surviving the trip is another question. It turns out you don't need the black holes to recreate this phenomenon in the lab, because fundamentally it is about the teleportation of information, not the warping of space-time. The experimental setup consists of two n qubits divided into n left and n right qubits, short of quantum bits. These sets represent the two black holes, left and right. The bits carry quantum information by encoding it in a superposition of states. That is, a qubit, unlike an ordinary bit, can be 1 and 0 at the same time until it is measured, at which point it collapses into either a 0 or a 1. Before it collapses, however, it can be used to do computations or even do quantum experiments, looking into the very heart of the cosmic computer, as it were. As with ordinary computers, it doesn't matter what actually encodes the information. Commonly, ions in magnetic traps are used, but they could be light particles, photons, or anything that has quantum behavior. The left and right qubits make up the sender and receiver side, with a small number, possibly just one qubit, on each end being the message encoder qubits. The rest of the qubits are carrier bits. A message is inserted into, say, the leftmost qubit, which is entangled with the other qubits via a complex series of entanglements. The message propagates, therefore, through all the qubits, apparently losing itself amid a chaos of fluctuating quantum states. Yet somehow the message will emerge in the rightmost qubit, about 80% of the time. At no point in the carrier qubits, however, is it apparent that the message is propagating. So what does this have to do with black holes and wormholes? It all comes down to a mathematical proof called the adhes-CFT correspondence, which shows a connection between anti de Sitter geometry and conformal field theory. In layperson's terms, that means that it connects certain kinds of geometries that might be relevant to the shape of black holes and wormholes, and field theories that concern the quantum mechanics of particles. It is important in string theory, but doesn't depend on strings. The correspondence between the qubit experiment and traversable wormholes comes specifically from a quantum state called the thermofield double, or TFD state. This state can be achieved between the left set and right set of qubits. It can also be achieved by two entangled black holes connected by a traversable wormhole. Thus, there is a real mathematical connection between the two ideas using the best physical theories we have: general relativity and quantum mechanics. There are some caveats here, but I'll get to those at the end. The University of Maryland lab, as described in a paper published in Nature last year, carried out this experiment using the same type of quantum states as in the black hole coupling, and indeed found that they were able to reliably extract the information. They were also able to test that scrambling of the message occurred in between. They did so using a simple 7-qubit computer using 9 ytterbium Yb ions in a trap. With this apparatus, they constructed quantum circuits that carried out the experiment and verified scrambling. Do black holes and wormholes really behave this way? One question is whether this experiment really tells us anything about black holes or quantum gravity. The answer is maybe. At most, it tells us something about quantum mechanics that we might be able to observe in real black holes one day, but probably not those formed out of stellar collapse, which have no real way of becoming entangled into two black holes. It may be that such pairs of black holes formed all the time in the very early universe. Thus, it could tell us something about how the universe formed that we could then verify in observations of the present universe. These could also be created in some future particle collider, though such black holes evaporate too quickly to be observed directly. Still, there is a lot we don't understand about black holes. We can only infer that the physics that takes place is what we think it is, and there is not some higher theory that we know nothing about. Another problem with the ADAS-CFT correspondence in general is that, as far as we know, spacetime appears to be de Sitter and not anti-de Sitter. Anti-de Sitter spacetimes give a cosmological constant that is the opposite sign of the one we measure for dark energy. That does not mean that it does not become anti-de Sitter at some smaller scale. It is just that at the scale of the universe, a de Sitter geometry is a better explanation. Nevertheless, it is a great achievement for quantum information theory and the theory of information transport that may help in the quest to create reliable quantum information networks in the future. And beyond that, perhaps quantum gravity. I think that one thing it does say about the physics of the 21st century is that we are about to find out how quantum physics exposes the operating system of the universe, and that a lot of otherwise unrelated phenomena are connected by the information they contain and how they transform information. Thus, this century will be the century where experiment and information merge to tell us a lot more about the universe than we could otherwise study, because the information is more important than the medium that contains it. Thank you so much for watching. See you again in the next video. Until then, as always, keep looking up, stay curious, and dream big.